name is Julia Oliveri, and today I'll be talking to you about graph algorithms, traversing the tree and beyond. This is the second in a three-part series. In the first workshop, we talked about what a graph is and what we can do with it, and in the next workshop, we'll talk about examples of graphs in the real world. If you have any questions during lecture today, you can feel free to message the chat, or if you're watching after the fact, you can email me. And the code we'll be working with today is at this GitHub URL, so you can feel free to pull that up and clone the repo whenever you have time. So first, a little refresher on what a graph is if you weren't here last time. A graph is a set of vertices and then a set of edges, which are just subsets of two vertices. You can basically think of a graph as a bunch of things, which are the vertices, which we also call nodes, represented by circles here, and edges, which are relationships between those things, represented by lines between the circles. Graphs show up a lot in the real world. For example, in social media, we get social graphs, where each vertex is a different individual, and edges are friendships between those individuals. They also come up in biology. A phylogenetic tree can be thought of as a graph, where vertices are different species or ancestors, and edges are the evolutionary relationships between those species. Even maps can be thought of as graphs, where different locations or cities are the vertices and roads between them are the edges. So one of the most basic things we want to do with graphs are graph traversal, which is essentially exploring the graph and maybe finding specific vertices in the graph. So if we have this example and we want to find the green vertex, what do? Of course, when we're just looking at the image, it's really easy to see. But if we can't look at everything at the same time, you can imagine just iterating through a list of all the vertices and checking which is the green one. But that doesn't take advantage of the structure of our graph at all. So when we're doing this, we're usually interested in algorithms where we move from one vertex to another. So you could also imagine just starting at a random vertex and then moving just randomly from edge to edge until you find the green vertex. But that's not a very organized way of doing it either. So we'll be talking about more specific algorithms for this problem. To understand graph traversal algorithms, we need to understand how the computer actually stores graphs. So there are many different ways to do this, and we'll talk about other examples in the next workshop. But for today, we'll just be thinking about the adjacency list or adjacency dictionary. And in this data structure, for each vertex, we store a list of all the neighbors of that vertex. So if we have this example graph, our adjacency dictionary would have each vertex and then a list of all the neighbors of that vertex. So the only neighbor of A is B. B has three neighbors, A, C, and D. C has two neighbors, D has two neighbors, and E doesn't have any neighbors, so it would have an empty list. So you can have this data structure in your mind when we're talking about the algorithms. You can see that it's really easy to find the neighbors of any given vertex, but we don't have larger scale representation of the structure of the graph from this data structure. So there are two main methods of graph traversal, the breadth first search and depth first search. So we'll start by talking about breadth first search. The way breadth first search works is that we search every neighbor of the starting vertex. So if we have 1 as our starting vertex, we would go to every neighbor in turn and check to see if it's the green vertex. After that, we would search every neighbor of the neighbors. So there's only one neighbor of the neighbors here. And we would continue searching outward in layers until we find our target vertex. So BFS is useful when we expect solutions to be close to the starting vertex because we search one layer at a time moving outwards. So one example of this would be if we're searching in a social graph for someone with the same job as the starting vertex. We would expect maybe they have many friends or friends of friends who have their same job, so it would make sense to search close by them rather than farther out in the graph. So the next method is depth first search. So in depth first search, or DFS, we start by just searching one neighbor of the first vertex. After we do that, we search an unsearched neighbor of that current vertex. And we continue searching unsearched neighbors of the current vertex until there are no more unsearched neighbors. So if we look at a more complicated example, we again start with the starting vertex, search an unsearched neighbor, search one of its unsearched neighbors, but if that neighbor doesn't have any unsearched neighbors, we backtrack back to this same vertex, and we repeat the algorithm. So after backtracking, we look for unsearched neighbors, which we can then follow until we find our target vertex. So depth first search is useful when solutions are expected to be very far from the starting vertex. So for example, if you have a graph of a game where your starting vertex is your given game state, and you want to search along all the possible moves for a winning condition to find a winning next move, you might prefer depth first search because you're only going to find wins in the very bottom of the graph. And so you would have to search for much longer if you did breadth first search compared to depth first search. So for example, if we had a graph of a tic-tac-toe game where we have our starting condition, and here the wins for X are circled in green, depth first search could probably find us one of the wins much more quickly than breadth first search, which would have to search each of these vertices before finding any wins. Now let's look at some coding examples of BFS and DFS. So if you've been able to successfully clone the repo, you can follow along here, or you can just watch on the screen and check it out later. So you can just open the graph search notebook and run each cell here. And here we have a definition of the BFS algorithm. So you can feel free to read this and look into it more carefully, but it's again just implementing what we talked about. We have our adjacency dictionary as input and our target, which is just a dictionary that given a vertex tells us whether it's a target, so a successful vertex or not. And we keep track of all of the vertices that we've visited so far in the algorithm. And we keep track of the layer we're on because, again, for BFS, we are searching outwards in layers. First the starting vertex, then all of its neighbors, then all the neighbors of the neighbors. So while we actually have vertices in the next layer, we move on to that layer, make it our current layer, and the next layer we initialize with an empty list. Then we search each vertex in the current level individually. We take all of the vertices that haven't been visited so far, that are neighbors of any of these vertices in the current layer, and then add them to the next layer, because they're what we'll be searching next. And then we check each of these vertices as we go along to see whether it's a success. If it's a success, then we return that vertex and we're done with the algorithm. Otherwise, we continue moving on layer by layer until we've searched the whole graph. We have an implementation of DFS here, which is implemented recursively. So again, this is just taking in our adjacency dictionary and our target dictionary. And what happens is we are just given a starting vertex. We check to see whether it has any neighbors that have not been visited yet. If it doesn't have any neighbors that haven't been visited, then we try backtracking to see if and we perform the same algorithm with the previous vertex. Here we can see we're backtracking. If we get all the way back to the start, and so that means that we've visited every vertex and haven't found any success. So we can return none as our answer. But if we do have unvisited neighbors, we can choose a next vertex. We keep track of the edge we just traveled on, so we're able to backtrack if necessary. And then we check the vertex to see if it's a success. If it is, we're done with the algorithm, we can return. Otherwise, we run the same procedure from our new vertex. So you can feel free to go more in depth with that test out the code if you're interested. So let's see what happens. Here are just some parameters defining a random graph, and we can see what that graph looks like. Here, I am coloring the vertex we'll be starting our search at as blue, and then each of the successes are green. And so looking at this graph, you can make a guess of which algorithm will find a success quicker, BFS or DFS. So let's see. When we try breadth first search, here the vertices that have been visited in the search are in gray. And you can see that we had to visit 24 of the 36 vertices before we found a success, this one here. We can see that layers were searched. Each of these layers didn't have any successes in it, so we had to wait till the fourth layer to find a success. Now if we try DFS, we only have to search 7 vertices before we find a success. Here we can see that because of DFS, we just continue going deeper into the tree until we can't go deeper anymore, and then we backtrack and we go deep again. And that was more applicable for this structure because the solutions were just at the very edges of the tree. Here I'm just showing it with the trees because it's kind of simpler to see, but this works for graphs as well, just general graphs. So now let's try to change the parameters and see what happens. When we try it with these parameters, we can see that there's a solution closer to the start. So again, we can guess whether BFS or DFS will result in finding a solution more quickly. And if we try BFS, we can see that we only need to search 2 vertices before we find the solution, since it's in the first layer outside of our starting vertex. But if we try DFS, we have to search this whole section of the tree, continuing to go deep, backtrack, go deep, backtrack. Because there are no solutions here, we have to search 22 vertices before we finally backtrack to our starting vertex, and then find a solution. So either now or after the workshop, you can try playing around, changing these parameters, seeing how these algorithms work on graphs that look different and have different distributions of solutions. So now let's recap some of the differences between breadth first search and depth first search. Breadth first search is good for when solutions are close to the starting location in the graph, whereas depth first search is good for when students are far from the starting location. Both of them have the same time complexity, which is at the order of the number of edges plus the number of vertices, and the same space complexity, which is order of the number of vertices. But breadth first search will always find the solution that's closest to the starting point, whereas depth first search doesn't necessarily find the closest solution. So next we'll see a different algorithm that actually makes use of graph traversal as part of the algorithm. Before learning about the next graph algorithm, we have to learn about a new graph concept. So far, we've just been talking about the simplest kinds of graphs. But imagine the situation where we're treating a map as a graph. We have a few different locations, and maybe our edges are the distances or routes between the locations. Well, if we think of the graph that we get, remember that graphs are just defined by pairs of edges. So this graph can also be drawn like this. And this image doesn't seem to really capture what we wanted to capture based on the map graph. Specifically, it doesn't capture the distances between locations. So if we want to encode that in our graph, we need a new concept, which is called a weighted graph. A weighted graph is almost the same as the simple graphs we've been talking about so far, except each edge also has a weight associated with it. So it's a pair of vertices associated with a weight. And So here in this example, we can see that each edge is given some number that acts as that edge's weight. And so this is how we could encode Euclidean distances between locations, potentially. This could also represent the strength of friendship or driving distance between two locations, basically any numerical quantity that is quantifying something about this relationship. So now that we're familiar with weighted graphs, we'll talk about the minimum spanning tree problem, which is essentially the problem of how can we find the tree connecting all the vertices in a graph that has the smallest total weight. So if you don't remember from last time, a tree is just a graph that is connected. So there's a path from each vertex to every other vertex, and it doesn't contain any cycles. So for some intuition about the minimum spanning tree problem, imagine we have 5 different houses, and we want to connect them with power lines. You can imagine this assignment of power lines where they are reaching every single house, but this seems a bit wasteful. This is probably more power line than we need to actually connect all the houses. If we do it in this orientation instead, the houses are still all connected, but we're using a much smaller length of power line. So this would be the minimum spanning tree in this example, where the weighted graph is just the weights on the weighted graph are just the weights corresponding to the Euclidean distance between each pair of houses. So specifically, a minimum spanning tree is a subset of edges of a connected weighted graph that connects all the vertices together, so we have a path from each vertex to every other vertex, without any cycles. So we aren't able to go from one vertex back to that same vertex following all new edges, and with the minimum possible total edge weight. So we're going to learn Kruskal's algorithm to solve this problem. So imagine that this is the graph that we want to find the minimum spanning tree of. The way the algorithm works is we first have to test whether the graph is connected. If the graph isn't connected, then there's no way we can find a connected subgraph of it. Looking here, we can see that we are able to make a path from any vertex to any other vertex by following edges, so the graph is connected. Next, we order the edges from the smallest to largest weight. So we can list them here. We can list ties in any order, but we have each edge with its corresponding weight sorted by weight. Next step in the algorithm is that we start with a graph with all of the vertices of the original graph, but no edges. So because this is a new graph, we can give it a new name, so we can call it T. Next, we proceed from the lowest weight to the highest weight edge. And whenever we have selected an edge, we try adding it to our graph T. If adding the edge causes a cycle, we remove the edge. And after adding each edge, we test if the graph is now connected. If it is, then we stop our procedure and we've found the minimum spanning tree. So how it works in our example is we'll start with this first edge, A to B. We add it. We check whether this causes a cycle. We don't see any cycles in this graph. And so we keep the edge. Then we test whether the graph is connected. We can see we actually still don't have a way to get from these vertices to any other vertices, so the graph isn't connected yet. So we try to add the next edge. So we'll add C, D next. So we again check for cycles. We don't see any cycles here. We check whether the graph is connected. Still not connected. We have 3 separate components. So we try adding the next edge. Again, we check if this causes a cycle, which it doesn't. We check whether it's connected, which it's not because E still is not part of the graph here. So we move on to the next edge. Now when we add the CB edge, when we check whether it contains a cycle, we can see that it does. We're able to move from one vertex back to the same vertex by not repeating any edges. So we remove that edge and we go on to the next. Now, after adding the CE edge, we check whether it causes a cycle, which it doesn't. And now we check whether it's connected, which it is. We can make a path from any vertex to any other vertex. So that means we have found our minimum spanning tree in this example. So it's a minimum spanning tree of weight 13 in this case. Now let's go over the full Kruskal's algorithm again. We start by testing if the graph is connected. Then we order the edges from smallest to largest weight. Then we start with a new graph that has all the same vertices of the original but no edges, which we call T. And then we test each edge starting from the lowest weight up to the highest weight, where we try adding it to T. If it causes a cycle, we remove it, and otherwise we check if T is connected, and if it is, we stop the algorithm and we found the minimum spanning tree. So if you're interested in a proof for why this algorithm always finds a minimum spanning tree, you can go on the Wikipedia page. This is also linked in GitHub to see the explanation. And also, it's a good exercise to try to think through intuitively yourself first. So when we're looking at this algorithm, it was easy to perform just looking at our small example, but it's not as clear how to do all of the parts when we have our graph stored in an adjacency dictionary like we talked about before. So specifically, testing whether the graph is connected isn't obvious. Given just like a long adjacency dictionary of vertices and their neighbors, how can we determine whether the graph is connected? We can actually do it taking advantage of our graph traversal algorithms. So we can run either DFS or BFS from any vertex in the graph. And then if that algorithm visits all of the vertices, the graph is connected. If not, the graph isn't connected. So if we had this graph, for example, we could run DFS starting here. We would end up visiting these 4 vertices. So we would know that we'd visited 4 vertices based on our graph traversal algorithm. And then based on our data structure, we can count the number of vertices in the total graph. And if they're the same, the graph is connected. Here, we would have visited 4 vertices out of the 5 total, so we know the graph isn't connected. If we go back to the algorithm again, another part that's not so clear is this part where it says if adding an edge causes a cycle, we remove the edge. How do we know whether adding an edge causes a cycle to be created in our graph? We can again use graph traversal algorithms to figure this out. So if we start with this graph again, we can run DFS or BFS from any vertex again. So if we ran from here, we would end up finding all 4 of these vertices. So we find all vertices that can be reached from this vertex by a path in the graph. That's also called a component. So this graph has 2 different connected components because there are 2 clusters of vertices that can all reach each other through paths on the graph. So once we do that, we again have our list of visited vertices in the given component. And once we have the list of vertices, we can count the number of edges between them just by going through our adjacency dictionary and summing up the edges only for the vertices in the connected component. Then, if the number of edges that we count up are greater than the number of vertices that we visited in that component, -1, the graph contains a cycle. And what this is taking advantage of is a fact that we talked about last time, that connected graphs without any cycles always have n-1 edges. There's a link on the GitHub for a proof of that if you're curious. This is another one that's interesting to think about also to gain more intuition with graphs. So this is a way of using our graph traversal algorithms again to determine whether a graph contains a cycle. This whole procedure is repeated for each vertex that hasn't been visited yet, and that lets us see whether each component contains a cycle. once we find a cycle in any one component, we know that the graph contains a cycle, and so we can stop the algorithm. Now let's look at the code for Kruskal's algorithm. So if you go back to the graph search notebook, to the minimum spanning tree section, you can run the Kruskal's algorithm definition cell, and you can see that it takes in the adjacency dictionary and weights on the edges, and performs the steps we just talked about. So the edges are sorted in an increasing order by weight, and we start by initializing a new empty graph with all the vertices that were in the original, but no neighbors for any vertex. We check whether the graph is connected. If it's not, we just return none because we can't find a minimum spanning tree. And otherwise, while the graph isn't connected, we take the next edge in our list, try adding it to our tree that we're building. If adding that edge causes our graph to contain a cycle, we remove it. Otherwise, we keep track of the summed additional weight from that edge, and we continue on with the algorithm until the graph is connected. And we can see here the algorithms for the testing whether the graph is connected, like we just talked about. So here you just run DFS from the first vertex or any vertex to get a list of all the vertices that are visited from that starting vertex. And then if the length of the visited vertices is less than the number of vertices in our adjacency dictionary, we return false. The graph isn't connected. Otherwise, we return true. And to test whether a graph contains a cycle, we again take in our adjacency dictionary. We then keep track of all the vertices that have been unvisited so far during the algorithm. And while there are still remaining vertices that are unvisited, we perform DFS from one of those unvisited vertices. We then count the number of edges between vertices that we just found based on the component that DFS just returned. And if the number of edges in the component is greater than the number of vertices we visited minus 1, we return true. There is a cycle in the graph. Otherwise, we just repeat for the rest of the unvisited vertices. Now let's look at some examples. If you scroll down here in the minimum spanning tree section, you can see this block of code contains some parameters that you're free to change to get different examples if you want. So here, we'll be creating a random graph and then running Kruskal's algorithm to find the minimum spanning tree. So if we run this is the graph that was generated. So here the vertices are in gray circles, and the weights on each edge are just written in the middle of the edge. And you can see that the thickness of the edge corresponds to the weight. So 7 is a bit thicker than 5. And you can kind of look at this graph and try to think about if you could come up with the minimum spanning tree. But if you scroll down, you can see highlighted in orange is the result of running Kruskal's algorithm on this graph, and we can see the minimum spanning tree. So here we can see that all 3 edges that weren't picked as part of the minimum spanning tree have weight 7, which is the largest weight in the graph. And the graph connects all 5 vertices, and there are no cycles. If we try a different example, this one is more complicated. This one, it would probably be hard to come up with on your own if you weren't following any specific algorithm. Again, edge weights correspond to the edge thicknesses correspond to edge weight. So you can see 2 is much thinner than 9. So if we scroll down here, we can find the minimum spanning tree highlighted in orange. We can see that the edges that weren't chosen have relatively large weights, 9, 8, 7. And where edges with large weights were chosen, such as the 8 here or the 8 here, it's because there was no other way to reach these far-flung vertices without using an even higher weight edge. So again, you're free to change these parameters and see what happens for different shapes and sizes of random graphs. Kruskal's algorithm has a time complexity of order the number of edges times log the number of edges. And that comes from the sorting step of the algorithm because that dominates the time complexity for the whole algorithm. And the space complexity is order of the number of edges plus the number of vertices because we have to keep track of all the vertices and all the edges for this algorithm. So now we're going to talk about the traveling salesman problem. So imagine you're a paper boy who lives at this house, and you have to deliver papers to each one of these houses and then end up back at your own house. The solution, the shortest path you could take that starts at your house, visits every other house, and ends up back at your own house, is called a traveling salesman tour. And the problem of trying to find that shortest path that visits all vertices but ends up back at the same vertex is called the traveling salesman problem. So this might be the solution to the traveling salesman problem for this small example. So again, the traveling salesman problem is the problem where we try to find the minimum weight path that starts and ends at the same vertex and visits every vertex in the graph. So again, the traveling salesman problem is the problem where we try to find the minimum weight path that starts and ends at the same vertex and visits every vertex. So this depends on having a connected weighted graph. This problem is actually NP hard, so there's no known polynomial time algorithm to solve it. And it's not been proved yet whether there's a solution that has an algorithm with running time less than 1.9999 to the number of vertices. So there's not a quick way to solve this problem for any large number of vertices. This is where approximation algorithms come in. Often we have problems that are NP hard, but we still need to have solutions, or at least close enough solutions to them, for many different applications. So when a problem's NP hard, approximation algorithms can be used to get solutions that are provably only a factor away from the optimal solution. So if we let the optimal value be called opt, then if we're trying to find a minimum, like opt is the minimum weight traveling salesman tour, for example, a K approximation algorithm is an algorithm that returns a value approx such that opt is less than or equal to approx. We know this because opt is the optimal solution, so it's the minimum possible. But approx is less than or equal to K times the optimal solution. So let's return to the traveling salesman problem again. Let's say we know the optimal solution here. If we just delete an edge from this cycle, we still have a connected graph. And so it results in a spanning tree of our original graph. Now, we already have an algorithm to find the minimum spanning tree of any graph, any weighted graph that's connected. And we know that that algorithm runs in polynomial time. And because we have a spanning tree here from deleting one edge from the traveling salesman tour, we know that this spanning tree must have weight at least equal to the minimum spanning tree. Otherwise, this would be the minimum spanning tree. So let's go back to our minimum spanning tree algorithm and see what it gives us. So we have this minimum spanning tree to reach every vertex with the smallest sum of weights across the tree. So we know that this length here must be less than the optimal traveling salesman tour. So how can we turn this into a traveling salesman tour? Well, we can actually just double every edge in our minimum spanning tree. Then the Paperboy can just go along the spanning tree until he reaches the end, and then double back across every individual edge. This gives us a traveling salesman tour, and because we know that the minimum spanning tree has weight less than or equal to the optimal solution, we know that our approximate solution will have a weight less than or equal to 2 times the optimal solution because we're just doubling the weight when we double the spanning tree. So the best known approximation algorithm for the traveling salesman problem actually has k about equal to 1.5, a little bit less. So the two approximation algorithm isn't too far off from the best that's known. We're going to finish up with one more fun example. So the Steiner tree problem is related to the minimum spanning tree problem. It's phrased as, given a weighted graph and a subset of the vertices of the graph, find a tree of minimum weight that contains all vertices in the subset, though it can contain more. So what this basically means is, let's imagine we have these 3 vertices. We want a minimum spanning tree that contains these 3 vertices, but we're allowed to add extra vertices if it helps make the spanning tree have smaller weight. And here we can just assume that the weights are the Euclidean distances between the points, and any pair of points can be connected. So we can imagine that this spanning tree might be minimal. If we were only allowed to use edges between the vertices we already have, this would be minimal. But in the Steiner tree problem, it actually turns out to be minimal to add a vertex right in the middle of the 3 vertices, and then connect each vertex to that middle vertex. Then the sum of the weights, in this case Euclidean distances, of each of these edges is actually smaller than if we did the V-shaped problem from before. So the Steiner tree problem is actually also NP-hard, but SOAP is able to approximate the right solution pretty well. Here, this person has 2 pieces of plexiglass with 3 screws in them, which represent the Steiner vertices, and we can see what happens. Just putting that contraption in soapy water, the soap bubbles actually create that middle vertex, just like we saw in the example. For the 4 vertex case, we can again see that 2 points are created correctly. And this even happens in the 5 vertex case. So this doesn't get the provably correct answer every single time, but it's still interesting to observe these problems being solved in nature by natural phenomena. All right, we've reached the end of the lecture. So now I hope that you've gotten some familiarity with the different graph algorithms and how they can build on each other to create more complicated algorithms. If you're interested, the next workshop at the end of August, we'll talk about examples of graphs in the real world. And if you have any questions, you can put them in the chat or email me. And I'll leave these last few minutes for you to play around with the code in the Jupyter notebooks, change the parameters, and ask any questions you might have. So thank you so much for watching.